It's okay. So it's 2:32, and I think I'll start. But Dr. Eick may have already talked to you about supervised learning. Well, learning is generally of two different types. And what do I mean by learning? Learning means building a model that predicts your input data. That's essentially what learning is in the context of data science, in the context of computer science. But models are not perfect, right? No model can perfectly represent the real world, because if you are able to create a model that perfectly in all aspects represents the real world, you've recreated the real world. So there's a paradox there. So what we want is the best fit model. And there are two fundamental ways of going about it. One is where you don't know what the real world, what the levers behind some real world phenomena is. That's when you use unsupervised learning, because you don't know what you're learning. And the other is supervised learning, where you know what how the world works, how the data is supposed to behave. And so when new data comes in, your model is able to effectively work on that and perfectly, or at least close to perfectly, recreate uh, the known data, the known attributes. That's all there is to it. So for supervised learning, the big difference is that uh, you have some idea, or you have a very good idea of what your output should be, of what the output of your model should be once when you're starting to model the big data set. Now, this is fundamentally very useful for known fields, right? So the way this works, the way a supervised learning approach works, is that first you need this known data, this known regularization of the entire world. Then you learn it using whatever model you want. Your model can be a neural network. Your model can be a decision tree. Your model can be a support vector machine. Your model can be as basic as a simple polynomial function that comes closest to the data. But that's when you learn it. And once you are like sufficiently, you have learned the input data, then you try to predict on new unseen data. That's pretty much all there is to it. So a couple of examples of how this works in practice. This is from Dr. X slide. So you have a table, you have a data set like this. Then you perform induction on that. You clean up the data set. You figure out what are the properties that are important to you, and then you learn those particular properties within that data set, and you eventually create a model. Then you apply that model on a test data set, and you get a class out of it. It's as simple as that. What does it look like in practice? Well, this is a spam email detector. You can see there's an spam email on the right, a very realistic spam email. But how does a spam email detector in the real world work? Now, the model that I've shown here is it's not one of the latest models, because you can see it's pretty slow. In the model inference service, you can see that the two filters takes 50 milliseconds and 200 milliseconds to perform. That is far slower than how Google spam filters or Outlook, Hotmail's spam filters work. They work in the terms of tens of milliseconds. So this is kind of old, but you can see how it works. So a spam email detector, which is a kind of a supervised learning approach, what it does is it takes your regular emails and it has a big database of spam emails. If you have the internet, you can look up something called the spam assassin data set, which is a very classic data set when you're trying to learn how to detect spam in your email. And using something like that, you parse your incoming emails. So you figure out like what parts of the emails are present in normal emails, and which parts of the emails are present in abnormal or spam emails. So you separate out those things, then you send it to some kind of inference service. Now the inference service, these days it's mostly machine learning models, very big machine learning models, but they are fundamentally Bayesian services. They are fundamentally very naive Bayesian-based systems for understanding for predictions, right? So they are very probabilistic predictions for detecting spam. And once you have detected that, you move on to whether you deliver it to a person's inbox or whether it goes straight to quarantines or blocks or whatever. And then this cycle repeats. So these three middle parts, the feature extraction service, the model inference service, and the action router, those are the systems that you see here. That's the training phase, the learning phase, and the prediction phase. Today in this class, what we are most important, what we are most interested in is the learning phase. And that's what we are going to talk about and why we need it, how we need it, et cetera, et cetera. So there are lots of different classification techniques for this. Dr. Eick might have talked a little bit about decision trees. There are rule-based methods, which you might be talking about. There are very simple classifiers like nearest neighbor classifiers, which we have all learned. Neural networks, which we'll be talking today. There are Bayesian belief networks, support vector machines, and all sorts of ensemble methods that take in all these different things, combine them together to get a better result. That's not always the case that an ensemble method is going to outperform a pure rule-based method, but sometimes it's the case. So that's how it works. So uh, today, neural networks, people mostly think about machine learning, right? This is the kind of thing. Wait, hang on. This video is supposed to be playing. I don't know why it doesn't. Yeah. So what a neural network works in the abstract is essentially a black box, right? So a big machine learning model that like the kind of thing that Google's Deep Dream project is, you have no idea how it's modeling the world uh, within within the entire system. It's just tens of thousands of huge tensors, tens of thousands of huge matrices of weights, essentially. And because you don't know how those weights, what all those individual weights mean, it becomes very difficult to predict how it's going to work in cases that it has not seen before. So to understand how this kind of output is generated, we must first go back to the very basic principles, the first principles, which are neural networks, essentially. So neural networks came about first in the 40s, just during the World War. It was first, the idea of it had been present before, even in the 19th century. But the most concrete example came from McCulloch and Pitts. The McCulloch-Pitts neuron model is essentially the first mathematical model of a neural network. Warren McCulloch on the right was from University of Illinois at Chicago, and Walter Pitts was a logician, and McCulloch was what in those days they called him a cybernetician, which is a term that has gone out of date these days, but that's what he used to call himself, a cybernetician. They were building on Alan Turing's work on computing numbers, and so what they did was they found out a way to describe how the human brain works or how neurons work in very abstract terms. And they showed that these like very simple basic elements connected in a neural network like this can eventually lead to very powerful computational abilities. At that time in the 40s, the machines ENIAC and other supercomputers were not strong enough to essentially deploy this kind of neural network that they were envisioning. But later on, John von Neumann, Norbert Wiener, and other scientists made sure that made something out of it. Even then, it took essentially up until the 80s and 90s for neural networks to take off. So the first model of the in the 1950s that came up was the perceptron model. At that time, it was a single perceptron. You learn about multi-layer perceptrons today, but at that time, the first things that came out were the perceptron models. But because computing power hadn't been able to catch up to what they were promising, the field essentially declined in the 60s and 70s towards more statistical models. So people were hard modeling through Newton's methods and Fourier methods and all other kinds of very hard statistical methods. And the neural network model fell out of fashion. Certain algorithms and computing powers breakthroughs came up in the 80s, and that's when it became really, really popular. You may have heard of people like Geoffrey Hinton, David Rumelhart, Ronald Williams. Geoffrey Hinton won a Nobel Prize recently, I think. So those are the people in the 80s who essentially broke through neural networks. But why would we need neural networks for a supervised learning approach, right? Why are neural networks one of the options for a supervised learning approach? Well, the answer to that is something called the universal approximator, right? What a universal approximator is is that a model that no matter what kind of input you give it is able to exactly predict the output of it. So you have a known set of inputs and you have a known set of outputs. A universal approximator will, in every single case, be able to take that known input and transform it into the known output. That's essentially what a universal approximator to any arbitrary degree of accuracy. Um, uh, Essentially, a universal approximator is what an ideal machine learning model is, where it learns all the possible relationships between any input and any output, given enough data, given enough architecture, et cetera, et cetera. So John von Neumann, George Box, these are the people who first worked on universal approximators. That's why their quotes are there. All models are wrong, but some are useful. And truth is much too complicated to allow anything but approximate. I like these quotes. Von Neumann was a smart person. So the universal approximation theorem that came out in 1991, but was known beforehand as a more fuzzy thing, states that a feed-forward neural network, what these terms mean, I'm going to explain later, with a single hidden layer containing a finite number of neurons can approximate any function to any accuracy. So essentially what this means is that if you have a single layer neural network, where it's just input, one hidden layer, and an output, any given function, if the neural network is big enough, it can approximate anything, theoretically. This was essentially the start of neural networks being used for various kinds of statistical purposes. Because by adjusting the weights and the biases of all the neurons within a single layer feed-forward neural network, highly nonlinear relationships can be modeled. And that essentially helped us solve various different problems. Now, neural networks are not the only system, or not the only model that can do this, right? That can solve the universal approximation theorem problem. You may or may not have heard of support vector machines. Support vector machines can do this as well. Fourier decomposition can do this. Simple polynomials, if you have a big enough polynomial, can do this. But the big difference between all these different methods of universally approximating any input, support vector machines, polynomials, Fourier decomposition, you can actually think of other things as well, other mathematical structures that can solve, other statistical structures that can solve this kind of thing. The big difference for neural network is that they don't have to be big. The more layers you put on it, the more parallel computation it performs. Even a smaller neural network can approach the kind of accuracy that a 10,000, 20,000 layer Fourier decomposition model would need. Actually. So that's a big breakthrough of neural network. That even a smaller neural network converges very fast towards an accurate solution. So, say for example, in the spam email detector system, if you train support vector machines to detect spam, it's going to break every time someone, because a spam detection, as opposed to many other kinds of supervised learning methods, is an adversarial problem, right? So anytime you manage to create a detector that stops all spam from coming into your inbox, the people who are sending the spam are going to learn that, and they're going to recreate the spam emails so that your detector is no longer able to catch it. So there's an adversarial fight between spam detectors and spam creators. But a neural network can fight against adversarial things. But a support vector machine or a Fourier decomposition machine or a simply polynomial-based machine is going to find it much harder to react to any kind of adversarial attacks on its surface. Another major advantage of neural networks is what I talked about earlier, is that it can model nonlinear systems very easily. Like modeling linear systems is also difficult, but it is much simpler because linear systems have hard cutoffs. So you can essentially do band cutoffs if you have studied in electronics, band filters, low pass filters, high pass filters. Those are essentially almost always good enough to deal with linear structures. But nonlinear structures, a low pass, a high pass, a band pass filter cannot deal with. So anytime your function, your input data is not linearly separable in one dimension, um, you need something like, in this case, you need a function like this. Say, for example, you would need a neural network to solve it. As long as your data is inseparable in different spaces, in low dimensional Euclidean spaces, in high dimensional Euclidean spaces, as long as your data is separable in some space, a neural network will eventually converge into that separation boundary, like this. So now this is the very basic neural computational model that Macaulay-Pitts came up with in the 1940s, and this is very simple, right? So you take the incoming weights and then you multiply them together and you subtract any bias from it, and you get a gate like this. We're going to work through these problems, but not these basic problems, but you can see that very simple linear functions like an AND or an OR or a NOT it can be solved this way. It can be solved using a single linear threshold, right? But the problem comes when you have more complicated, when you have a XOR, right? When you have an XOR, how do you separate this? Right? Because in an XOR, a single decision boundary, like the one that you saw, cannot separate this, right? At least in a 2D space, this cannot be separated using a single decision boundary that you saw over here. Like the kind of boundaries that you're seeing here cannot be separated. So for a XOR, what you need is something like this. You need two multi-layered neural networks. You need two units so that each of those units biases can pull the decision boundary in different ways. And so what happens is that it is able to essentially carve out the 2D space into a universal approximation of the input. And this is a very simple, like the XOR case is very simple, but it can eventually obviously it can get much more complicated. And that's what an artificial neural network is, right? So if you're a practitioner, that is, if you don't need to know what the black box is, all you need to know is what the input is and what the output is, and the interior of the artificial neural network organizes itself so that it is able to solve this. So you can see that it's a very simple system, right? So the threshold here, the sign, modulus actually, and what it does is it takes all the input values x1, x2, and x3, multiplies them with the weights, which is 0.3 here universally, and then you have a threshold value of 0.4 to bias your output in any direction, and that essentially gives you the correct answers every single time. So no matter what kind of input comes in, it's going to give you the correct output. So what you see very important here is this activation function over here, right? Because this activation function over here essentially flips the input. So because you have a nonlinear, because this combination can become very much nonlinear. It's just one layer right now. If you have multiple layers, and go into very much nonlinear. But it has to clamp to a result. It has to converge to some value, and that's where the activation function comes in. This function over here comes in, and there are many different ways of activation functions. There are sigmoids, there are tans, there are sine functions, there are linear functions, there are ReLU, rectified linear units, and etc. So based on the neural network topology, you have different kinds of activation functions that are used for solving this. And this activation function, the final function that you see here, that is in a sense the universal approximator that I was talking about, because that is what is taking the input, processing it, and giving it to you as a known output, essentially. What are hidden layers that I was talking about? The intermediary layers between the input and the output layers are the hidden layers. So in this case, all these H3 and H4, these are hidden layers. They are called hidden because from the perspective of the input and the output, you don't know what's in there, and you don't need to know what's in there. All you care about are the input and the output. So that's why they are hidden from view. So they are called hidden layers. In a more complicated neural network model, such as like a large language model or any other kind of like image detection model, image segmentation model, all these hidden layers are going to be neural networks of their own. They're going to be fairly large UNet structures and LoRa structures and other much larger complicated structures of their own, and so on and so forth. So you don't need to, hidden layers means for the purposes of testing out the model, you don't need to know what's in there, right? So this is essentially the basic general structure of an artificial neural network. You have an arbitrarily large input layer, you have some number of hidden layers, and then you have one output layer, essentially. So if you're writing a neural network on your for your code, what you have to be very careful about is this calculation, is this shrinking, right? Whether if you have multi-class classification, for example. So if you're simply for a spam detector, all you have is an email a spam or is it not a spam? So it's a yes or no. But you can have classifiers that are multi-class. So you might need to classify something in the same example. Say your email is coming in and Gmail wants to send that email into one of various different folders, whether it's a promotion, whether it's a primary email, whether it's a forum email or whatever. So in that case, you have multi-class classification. So your output layer is going to be larger. It's not going to be just one. There are various different ways of doing it, but that's one basic way of doing it. So, and what do we mean by training a neural network? It means learning the weights. And there are various different ways of learning the weights. In a feed-forward neural network, as you progress from the input layer through all the hidden layers to the output layer, you keep on learning the weights.
Can you go over classified?
I'm sorry?
Can you go over classified?
The multi-class thing? Multi-class means like in the output, like in the spam email I explained, like your output of a neural network, given all the inputs, can be true or false, yes or no, things like that. But in various other cases, in various other real-world cases, your output can be more than that. Your output can be it's class 0, it's class 1, it's class 2, it's class 3. So in that cases, your output layer is going to increase. The size of your output layer is going to increase because you have to account for all of them. And your activation function is going to change because if you use say, for example, the sign activation function from here, this is not capable of dealing with, where is my mouse? This is not capable of dealing with multiple classes because it just breaks it into two. So your activation function is probably going to be rectified linear units in that case. Right. So yeah, when you're learning a neural network, you're learning these weights. And you learn these weights in a feed-forward neural network, you learn these weights as you move along. In a backpropagated neural network, which is every single neural network these days, you also correct the weights coming back. So you adjust the weights going forward, and you see what the output you're getting. And you're seeing that the output that you're getting from your neural network is very far away from the actual output that you want. So you go backwards, and then you correct the weights again. That's what's called backpropagation. So you backpropagate the errors. We're going to talk about that later. So that's what we mean by learn. Now, this slide has a bunch of different terminologies that we use. I'm not going to go over all of them. These are fairly obvious, but I just put these in there because these are essentially exam prep. So like some of these questions might come up in your exams. So this is just for you to go over to understand like, okay, this is what these things mean. This is what an activation function is. This is what feed-forward neural networks are. This is what learning is, essentially. So what is we need to work on a neural network, to solve a neural network, we need to first define, right? How do we define a neural network? Well, a neural network is a function from X to Y, where X is all rational numbers, and the output is a real valued, discrete valued vector value target function, essentially. So we are approximating, we're trying to approximate a class of rational values into a different class of real valued discrete values. which is our classes. True or false, class 0, class 1, class 2, class 3, etc. etc. And this is how once we are feed forwarding, once we're moving forward, this is how these are calculated. So sign in this case is the activation function, which is if it is greater than 0, it's 1. If it is less than 0, it's -1. We take, in this case, what we're doing very simple. We're taking the input, we're taking the inputs, multiplying it with this weight, and we're taking this input and we're multiplying it with this weight, and we're getting this the value of this sitting there. And then we subtract. We do this for both of them, and we subtract a threshold value from it if there is, and the output is again this multiplied by this, and between this multiplied by this. So all your trainable parameters, because these are essentially values that you're calculating. These are your input values, and your output is something that you know that this is what this is what you want your output to be. So the values that you're training are these weights. W13, 14, 3, 2, 4, 3, 5, 4, 5. So this is your essentially your entire trainable parameter. So like I said, it is because of how the universal approximation theorem works, neural networks are very powerful, very effective general purpose supervised learning method. Obviously, we don't really use base neural networks these days for actual statistical purposes. We use more powerful machine learning models, more powerful deep learning models, but to get there, you have to understand the basics. Where do we start? And can you calculate by hand all the values that it's calculated? It is very useful. Like in my case, because my work is essentially in geostatistics, in geosciences, geoinformatics, I get a lot of sensory data from, say, satellites, from airplanes, from drones, or whatever. So in most cases, all this data needs to be collated, and you need to find out some information from out of them. Before machine learning models came out, geostatistics was a field that nobody wanted to go into because the results were very up in the air for a lot of the times. But right now, with neural network architectures, they're way better. The best learning method that we know that came up in the late 80s and early 90s, which made neural networks so powerful, is the backpropagation algorithm, right? So where does the backpropagation algorithm come in? So these threshold units, in this case, whether it's a sine function, whether it's a modulus, whether it's a rectified linear unit, whether it's tan H or sigmoid or whatever, those are the threshold units, and you need them so that you are able to introduce, because when your input data might be linear, might be nonlinear, and these threshold units are what is introducing that nonlinearity into your neural network. Without this, you cannot take a nonlinear data set, convert it into classes without having some kind of threshold unit, right? The problem with many of these threshold units, many of these activated functions, is that you can see it here, right? This threshold function t that you see here, that's the sine function. It is able to introduce nonlinearity, but it is not a differentiable function, right? So learning in many cases, as you'll see, that gradient descent is probably the most common way of learning neural networks, but I'll talk about gradient descent later. But the reason why some of these activation functions are not useful is because they are not differentiable. And because if they're not differentiable, the problem is it becomes very hard to know how it's converging. One of the ways differentiation is very helpful in cases of neural networks is that once you have run a neural network, once you have run these things and you have an output, then you know that you're very far from the input or you're very close to the input, right? And then you correct your neural network so that your model is moving towards the correct input. If it's consistently giving you wrong classes, then you know that we need to change something in the approach. We need to change something in the way to make it move towards that. But how are we moving? How do we quantify that movement? Like if we change some weight somewhere, the neural network would move an arbitrary amount of either towards or away from the correct input, the correct output. If we are unable to differentiate this output, then we don't have a gradient, and without a gradient, we don't know which direction it's moving. We don't have the direction of movement. Is the neural network, as we are changing the values, is it getting more accurate? Is it getting less accurate? Like how does this work? So in this case, we change up the activation function to use a nonlinear differentiable input output function like the sigmoid function or the logistic function to solve this problem for us. So because training a neural network is an iterative process. You don't just go through it once and back and then you're done. So if you're running on the data, then you are slowly converging on some accuracy low point, and that's where you need some kind of differentiable activation function to solve this for us. These are two very common ones, right? This is the output of a sigmoid or a logistic function, and you'll find that in the real world, most of them use some variant of this of this purpose, right? So what we have learned is that any of the like AND gates, OR gates, NOR gates can be represented by a very simple two-layer network. Any continuous function can be approximated by a two-layer network, which is the universal approximation theorem. Sigmoid functions provide a set of basis function or threshold units or activation units from which any arbitrary function can be composed. And if we have three-layer neural networks by the universal approximation theorem, any input function can be approximated to an arbitrary amount of accuracy. So let's do a small quiz. So how do we do the prediction? Very obvious, right? If we have a neural network, as you see on the right, how do we do? If we give it a new data, then how does the prediction work? Once you have trained a neural network model, you have this model. So how do we perform predictions on this? Yeah, essentially, yeah, you give it an input and you run through the model one more time, but this time you don't change the weights. The weights remain fixed. So once you have learned a model, everything freezes, and that's how you start using it for predictions. So what do you need to fully specify a neural network? Like if you want to define a neural network in a computer or as a mathematical term, what do you need? Yeah, the weights. Yeah, that's all you need. That's why even if you have like huge neural networks, huge deep learning models, ChatGPT, Claude, whatever, their basic model, which is like tens of thousands of millions of matrices, all those tensors, those are just weights. That's all you need.
What about the biases? Is not needed, or are those included?
Those are included within the thing. Like that, the biases depend upon, like in the black box itself, it doesn't care about any bias. You add the bias to the end of it. Like to define the model itself, all you need are weights. And then if you want to change the output of the model slightly, you add in or subtract biases from it. But to define the model itself, you need nothing but the weights. That's all you need.
So how do you determine the number of weights? Sorry, I don't know if you want to go over it yet.
Well, that depends on that is dependent on you, right? You start with a very basic, start with a three-layer MLP, right? And then you start building on it. If your three-layer is taking like 10 hours and hours to converge to a suitable accuracy, then you start increasing it. Right? So it depends upon you. So I think I talked about this, but why do you think these predictions neural networks are very fast compared to, say, support vector machines or
fast.
Yeah, they converge fast, but why do you think that is? More layers, but what does more layers mean? It's parallelization. Yeah, it parallelizes the solutions. So in case of like Fourier solutions or support vector machine solutions, the single line of the support vector machine calculation is all there is to it. But neural networks are massively parallel, and that is the big advantage of neural networks. And what makes it expressive is something I talked about just now. It is, I'll tell you right now, it's the nonlinear units. It is the support, the functions that we saw, the sigmoid function, the logistic function, the tangent function. That is what gives it the ability to take a nonlinear function and accurately predict it. So let's train a neural network, right? Let's go through this step by step, because in your exams or whatever, you might be asked to solve one of these. But so it's a good idea just to see how exactly you're calculating, right? So for a neural network, what you have been given is what you would initially be given are your weights. In this case, all the weights are 0.1 except W45, 0.2. Your gamma is given as 0.2 as well. In the training example, your inputs are 1 and 1, and your output is 1, and your activation function is a sigmoid activation function, right? Your learning rate is 0.2. So how do you go about doing this calculation essentially? So you go essentially step by step, right? So you apply the sigmoid function that's the mouse, okay. So you apply it to L1 times W14 plus L2 times W24. This is A4, which is the sigmoid function of 0.2, gives you 0.555. And you do this for all of them, right? You do this for A3 and A4, then you do this for A5 as well. So for A5, the value you've gotten is 0.647. What the value that you wanted given here was 1. So your error is 0.353. That's your error. So once you know the error, you need to move your neural network so that you're able to minimize that error. Right? And to minimize that error, we use something called gradient descent. And how does gradient descent work? Is because the activation function that we just saw was differentiable, so that every time we differentiate on that point, we get a direction of movement. So we make sure that every time we change the weights, we look at how this weight vector from the differentiation is moving. And at each step, the weight vector is modified in the direction that produces the steepest descent along the error surface. So your goal is to get towards W3, and you start from W0. And as gradient descent progresses, it finds more and more steeper gradients, and so it converges slowly towards W3, which is the minimal error. Now, another problem here is that your step weight. So if you step in too much, so you see how much we're stepping between W0 and W1, right? So in W3, if you step an equally large amount, you might miss the minimum, and you would find that then your gradient is suddenly decreasing again. So sorry, increasing again, and you have to be careful about that. And that's something that again, as computer scientists, that's your job to figure out. What kind of step weights do we need to use to figure out if we are truly hitting the. Yes, you change the rate of learning. That's one of the ways of doing it. There are various different ways of handling this, but rate of change of learning is one of the common ways of doing this. So yeah, this is the formula for updating the weights. This is not going to be like nobody does this manually, but you should know this because many of your if you are say building a very basic neural network to solve some kind of problem, you put it into ChatGPT, it gives you a fully solved neural network, and you run it and you try to see what's going on. You'll more often than not find that it is not converging to the value that you want. Right? It is it is giving you results, but it's not accurate. So if you are modifying a neural network and you're trying to figure out how to improve it, at the very basic part, you need to understand how gradient descent works intuitively. Because sometimes you'll find that changing your model in certain ways is reducing the error very fast. But that may or may not always be the best way, right? If you're changing your error, if your error is going on very fast, it could be due to multiple different reasons, and it's very easy to get stuck in false solution spaces. Essentially, because remember the solution spaces that a neural network is exploring is essentially like a big 3D field, right? And the solutions are like holes in that 3D space. So you don't know whether you're in the correct hole or not. So if you need to understand you need to have an intuitive understanding of how gradient descent algorithms work to figure out whether how your model is going towards accuracy, how your model is working is good enough or not. So always be very careful. Gradient descent is also sometimes called steep hill climbing approaches because it's essentially gradient descent is hill climbing. You're the quickest you are getting to the bottom means the slower you're climbing the hill. So these are essentially all the same things. The big thing here is, like you said, the learning rate is what matters in your neural networks, in your machine learning models, whatsoever, etc. Now, if you have a more complicated neural network where you have multiple hidden layers which are in themselves more neural networks, like in any kind of deep learning model, you'll find that your internal layers are again large machine learning models. They are going to have their own learning rates. So you're going to have delta learning rates and sub learning rates, and so these are all things that you are going to need to have to control for your model to work correctly. So yeah, and your error function is almost always differentiable, so you don't need to worry about that. So this is what it looks like if you're plotting your gradient field. So you can see that if your solution is in the exact middle here, if your origin point at 0, 0 is where your minimum error is. So no matter where you start, so your neural network first solution is not going to be at the origin point, right? It's going to start somewhere here. It's going to start somewhere in this big white space. And as gradient descent progresses, it's going to learn that this is how the gradient descent is. So it's going to move in the reverse direction. It's going to fall down this hill and it's going to try to figure out where this solution is. That's what gradient descent is trying to do. But again, like I said, there might be false minimas in a very large field. There might be multiple different places for solving this. So you have to be very careful that you're not trapped in one of them. So the problem with this kind of like big multi-layer perceptrons is that if we don't give feedbacks, how do we change the layers, right? So if all the activation functions are differentiable, then the output of the network is a differentiable function of the input and the weight, right? And an error function, in many cases, it's SSE, some of squares of errors, it's also MSE sometimes, and there are very different error functions. This error function also has to be differentiable because you are trying to do gradient descent on the error function, so you have to move on that error function as well. So then we can evaluate the derivatives of the error with respect to the weight and use these derivatives to find how to minimize this error function using gradient descent or other optimization functions. So the entire purpose of this part of the lecture was that the purpose of a neural network is to minimize this error, right? So that your input goes to the known outputs. And the way we do that is through gradient descent, and gradient descent needs your input and your error functions to be differentiable because that's how a gradient is calculated. So that just keep that in mind. So, and because we're using gradient descent, and now that we know the direction of movement, like we are going towards lesser error, then we also need to again update the weights. So we have reached the output, we have seen what the error is, and gradient descent has told us, okay, this is the direction of the error. So we need to minimize error by changing it this way. So then we again go back and we back propagate that error to all these different weights. And that system is called backpropagation. Backpropagation. So for backpropagation, you need to use the chain rule. Does anyone remember what the chain rule is for calculus? Yes. Yeah, that's essentially the chain rule, and this is what the backpropagation essentially algorithm uses, right? So what is the intuition behind it? Right. So you change the weights in the direction of the gradient to minimize error function. So you move from W0 to W1 to W2, and chain rule means you calculate the weights of the intermediate weights. So all the intermediate weights between the final weight and all the inner weights, and you memorize the weight updates to make the updates much faster. Memorize means essentially caching it. So you store the weight updates in a database so that you're not recalculating all these updates over and over again. So you cache. So this is how essentially backpropagation works. So there are two steps: the forward step and the backward step. So in the forward step, given the input, make predictions layer by layer, like the way we showed earlier. So you go layer by layer from this first step, from the input to the output. You just calculate all the weights. And then in the backward step, you hit the output, then you calculate the error, then you again update the weights layer by layer, but this time from the output towards the input. That's it. And this is essentially the algorithm for it. This is what I defined, but like in more mathematical terms. So this is something that is probably going to be in your exams, which is how do you update weights in a neural network, given that you have an activation function, an error, and you're backpropagating it once, right? So how do you do this? So this is the backpropagation example, right? So in the forward movement, you calculate A3 from L1 times W13 plus L2 times W23, etc., etc. Right. So that's how you do the forward calculation. A4 is W23 times L1 plus W24 times L2. That's how A4 is calculated. But how is A5 calculated? Again, the same thing. A3 times W35, etc. And then you calculate the error. Obviously, you will be given the A5 value, so you calculate the error from it, and then you calculate all the backpropagation weights from. Let me see. From here, so you see W5, delta 5. These are the backpropagation weights for the final value. Delta 3 is the backpropagation weights for A3. Delta 4 is the backpropagation weights for A4. Or H3, H4, it might be, the initializations might be different. So this is how you calculate it. Calculate delta 5 by taking the error, which the error is simply A5 minus the error, whatever value you get, and putting it through the error function. And then you multiply it with your activation function here. And then with the differentiated version of the activation function. Then you calculate delta 4 the same way, where you calculate delta 5 times W45 times G prime of Z4, and then you calculate delta 3 the same way. And once you have that, then you recalculate the weights, W13, W23, W14, W24. You recalculate the weights using this formula. That's all there is to it. So the first time you go through it, you get a value. And the second time you go through it, your error should decrease. That's the promise of backpropagation. So first time you go through it, you get a value of 0.647. Once you backpropagate these delta 4, delta 3, these weights, and then you update the weights again using these delta 5, delta 3, and delta 4 values. This time your A5 that you get is 0.66. So it gets marginally more accurate, marginally closer to 1. That's pretty much it. See if you can. I mean, these slides are going to be on Dr. Eick's website. make sure you're able to solve this, right? So this is going to be in your exams, and this is the very basics of backpropagation. If you're able to understand how this works, how this entire process works, then you should be able to solve any backpropagation problem. So again, I'm going through it from the front, from the start once again, just in case you were not able to follow. First, for any backpropagation example, the first movement is feed forward. So the values that were initially given at L1, L2, A3, A4, and A5. Sorry, L1, L2, and A5 are the values that you've been given. We calculate A3 by taking W13 times L1 plus W23 times L2, and then you apply the GX function, the activation function on top of it, right? So G times this multiplied by this plus this multiplied by this. You do this for A3, you do this for A4, you do this for A5. Same way. A5 would be A3 times W35 plus A4 times W45. All of it put into the GX function over there, the activation function that's given. Once you have A5, that is the output of your neural network. You would in the question itself, you would be given an output. So in this case, the output is supposed to be 1. But if you run this calculation, you'll find that the output that you're getting here is 0.647. Right. 0.647 means you have an error of 0.353. So now you're running backpropagation. How do you do backpropagation? First, you calculate delta phi. Delta phi is the error that you get multiplied by the differentiation of that function, of the G function, of whatever activation function you've been given. So the differentiation of G prime is Gx times 1 minus G over X. And you apply that to the value of A5, and that's how you get delta phi. You do that again to calculate delta 4, which is the backpropagation weight for this one, and you do that same thing again for delta 3, which is the backpropagation weight for A3. That is calculated as delta 5, which you just calculated, multiplied by weight. For this one, you multiply it by this weight, W45, times this hidden weight, A4, times 1 minus A4. And that's how you get this delta 4 and delta 3. Now, once you have delta 4 and delta 3, you are going to need to update those weights, W13, W23, W14, W24. How do you update those weights? This is the formula. So you take the initial weight and then add to it the learning rate multiplied by delta 3. And that's all there is to it. And then you have the updated weights, W13, W23, W14, W24. And once you have this updated weights, you run this neural network one more time to get what the changed values are. And you'll see that sometimes it has either improved, or in most cases it's going to improve. So it's going to give you a better, more accurate results. That's pretty much all there is to backpropagation. But this is not all there is to training, right? So one of the things that you have to be careful about is that neural networks don't guarantee convergence, right? It's going to come very close. It's going to come arbitrarily close to your solution, but it might ping pong. It's because of how gradient descent works. It might not settle on the absolute best value. It might ping pong close to the value. So you need to be careful about that. For more realistic problems, more real world problems, your networks are trained on very, very large amounts of values with tens of thousands of epochs, which is tens of thousands of iterations. In older days, these used to be run purely on the CPU, but modern GPUs, NVIDIA GPUs primarily, but also AMD GPUs, they have specialized tensor processing units on your GPUs, which are specialized for performing tensor calculations. And all these calculations that you saw in large scale, they're essentially matrix multiplications. So TPUs, modern TPUs are structured so that they're able to do this kind of matrix multiplications incredibly fast, much, much faster than your CPUs, for example. So, how do you end training? Well, there are many ways of ending training. You might have hard cutoffs of the number of epochs. So you might say that okay, no matter what your accuracy is, we're going to finish training after 50,000 epochs or after 10 epochs or whatever. Or you might have criteria like if your error is not changing by more than 0.1%, you're going to stop training. Or if suddenly once you're training it, your validation set error is suddenly starting to get high while your test set error remains low, then you're also going to stop. There are many ways of early stopping uh, to uh, to get to a good position training neural networks. And a big thing is to avoid this local minima problem where your solution space is very large and there might be various different solutions within that solution space. Some are accurate, some are less accurate, but there might be various solutions. To avoid getting stuck in one of those non-optimal solutions, generally a good idea is to start with different starting locations. So one of the good ways of doing this is not just your standard train test validation setup, but a good way of dealing with the local minimum problem is cross validation. So you cut out the data set into various different groups and you run your model on all these different groups of your data set. So that remember that image of the entire data set, which is essentially a grid. So you don't start on any one location and get stuck in one minima. You want to start all over the grid so that you always end up finding the best possible solution within that entire solution space. One of the big challenges of this thing for neural network is overtraining, overfitting. What happens is if you run your model, if you have less data and you run your model too many times on that, your neural network learns that data set, that given data set very well, and it is unable to generalize. And generalization is the entire purpose of a neural network. Generalization is the entire purpose of a data science research.
Question, is it like, let's say you have like a reasonably sized, like a big amount of data. Is there a chance of the neural network eventually overfitting that?
Yeah, if you keep training, it's going to overfit. Overfit means that if you give it new data, it is unable to work correctly because all it knows is the training data. So what the purpose of a neural network is that you have to give it some amount of leeway so that it is able to make some mistakes. And those mistakes are where it is able to deal with new data. That's why even if you have like small data sets, something that is very commonly done is data augmentation. There are machine learning models which augment your data set, which takes your existing data set and just like jitters it slightly so that you get like suddenly your data set of like 10,000 images or whatever gets bumped into 50,000 images and you train your model on top of that. So you have to, it is very simple to get stuck into overfitting, especially because modern models are so powerful that we are running out of data to train them. So in a lot of cases.
Aren't like big like AI companies now trying to go for like I forgot the difference between deterministic and non-deterministic, but wouldn't overfitting maybe resolve that issue?
Yeah, but the problem with overfitting is that the real world information is not always deterministic, right? So if you overfit on the training data, it essentially leads to like model collapse, right? Like your model cannot move outside of that information of that training information.
Yeah, I'm wondering if data augmentation should always be done at the start, or if there's a case for where you augment it each time for like each epoch.
No, you should. I mean, there are different schools of thought for it, but generally my experience has been that if you do that, if you do something like LoRa, where you augment the data set in various different steps after you run it once, like you said, and then you change up some of the input data sets and run it again. The problem is it becomes very hard to interpret the results. Like you don't know which augmentation is having what kind of effect it's having on the final data set. For image segmentation specifically, like if you work with medical images or geospatial images or whatever, you'll find that a lot of data augmentation is essentially taking the image and like rotating it 15 degrees or making it slightly blurry or changing the color slightly. And basic things like that. So they jitter the images slightly. And what happens is that if you add that in epoch after epoch after epoch, then you lose track of what changes is good and what changes are bad. So there are ways and means. You have to look at literature to see like what people have done previously and in that particular field and what is giving you better results. But in general, a best practice is you take your initial data set and you augment it. Then you run it. So that you don't bias yourself and you don't bias the neural network. Kind of. Yeah, there are various methods of training for looking out for overfitting and overtraining. Validation sets are very important. Generally, you see that you always do training and testing. But in a lot of neural network approaches, having a holdout validation set, so you split your data set into train, test, and validation. Having a validation set is honestly very helpful. So you don't test your model on your test set. Your test set is only used on a model once the model has been finalized. You test your model on the validation set. That's essentially a good way of finding out whether you're overfitting on it. You keep your test set out completely separately from the training. And obviously, like I said, cross validation is a really good idea for all of this. And well, there are many ways of overfitting prevention. Too many hidden units can often lead to overfitting. That is, your neural network becomes too complicated. Some cross-validation methods are very handy. Another approach is your weights are decaying. So every time after every epoch, a little percentage of your weights are lost, and so that makes it so that your neural network has some amount of non-determinism in it, so that it adds in a little bit of error into the neural network, makes it more powerful, makes it less likely to overfit. One really good idea by Hinton et al. Geoffrey Hinton is essentially the godfather of modern neural networks. His idea was dropout training. So every time you run the model, you delete some hidden layer with some probability P. So one of the hidden layers, one of the hidden units within your neural network gets randomly deleted. And that essentially keeps the neural network on its toes. And eventually, it generally leads to much better ideas. So without dropout, you can see that the classification error is much higher than with dropout. Dropout seems slightly counterintuitive, but it works because, again, it introduces randomness within your neural network. And overfitting, the entire purpose of overfitting is you lose randomness. Everything becomes deterministic.
And so we're dropping weights randomly just to reduce the chance of overfitting and
Yes.
increase the randomness.
Yeah.
But where is it going with this? But how does this affect our error, like classification error?
You don't know how like in this case, in this example, it's improving, but there's no guarantee that it's going to improve your classification error, right? The entire purpose of this is not error. It is to prevent overfitting or overtraining. Yeah. And overfitting always leads to higher accuracy. And less overfitting means that your accuracy is not going to be quite as high.
So if I drop a weights and then I do a back propagation again and I make new weights now for them, excluding the weights I dropped, wouldn't that affect the other weights?
Yes, it does. Yeah, that's why it's done. The entire model, the entire network slightly reorients itself.
Okay.
This is dropout is actually based on like human experience. Sometimes people who have like brain injuries, they learn how to they learn how to continue even despite it. So other parts of your brain takes up the weight. So that's what dropout was kind of based on, like human intuition, kind of. Yeah, this is essentially what dropout training looks like in the input space, and yeah, that's pretty much it for us. These are a couple of websites that lets you play around with it. This website, especially playground.tensorflow.org, lets you take in different like new activation functions, different input functions, etc., and lets you see if you change up the number of hidden layers, if you add in different layers, what the output looks like. When does it overtrain? When does it overfit? How does it stop overfitting, etc., etc. So Yeah, that's pretty much it for today. From this class, for your exams, generally speaking, the backpropagation is usually a question. So look at the slides on backpropagation and see if you're able to solve. What's up? Yes. Yeah. You know. In the real world, no, but in for
We just science, we had to memorize and
no, in Dr. Eick's exams, you're usually given all the information. Yeah.
thank you. How would the other questions look like?
For neural networks, you're probably gonna have a couple of like written questions, like based on the slide, like what is.
Besides just like, but we haven't had much.
Well, Dr. Eick's gonna talk about it. So, what's up?
So for backpropagation, should we expect multiple nodes in the hidden layer or layers?
No, you see the one that we got, you're gonna get something like that.
Just one layer, two layers.
Yeah, obviously, one hidden layer. One in this layer, one hidden layer. Yeah.
And I see.
And if you have questions about like neural networks, applying deep learning models or whatever, you're always welcome to contact me.